Welcome to a presentation on chemistry. This will coordinate with Chapter 1, Section 2, and this would be the second video of a 3-video series. Following, there are approximately 30 slides, and that includes this cover slide and an ending slide. This presentation, I will endeavor to make it as quickly as possible without losing information. But there are a few things that you can do in these presentations. One thing is that if you ever need to, I suggest that you pause. Pause the video. I will save it as a video because it's very difficult to deploy or to export just narrated PowerPoint presentations, which is what this is, in simply a PowerPoint format. And so I save it as a video and deploy it that way. So with that, though, you can pause it, and you can also mute if you don't need to hear me talk over the slides. If you just want to get the content down, by all means, please mute. That's fine by me. You may miss some of the content or some of the intention behind it, but that would certainly be up to you. And I strongly encourage you to pause the slide whenever you need to if you're recording notes from these PowerPoint presentations. And if you're watching this because you had an absence or you're out for any variety of reasons and you're trying to do some makeup work, I strongly suggest that you actually take notes as if you were in class from this presentation. This, for all intents and purposes, is the in-class presentation. I have added a couple of additional slides for the content of it because it's online, but there you have it. Okay, this corresponds again with Chapter 1, Section 2, Matter and its Properties. We've already had the student learning map, key learning, and the unit essential questions, so I will simply leave it at that. If you need this, certainly pause the slide and get what you need from that particular this particular part of the presentation. However, new to us is the concept for Lesson 2, which is what this is also, corresponding with Section 2. And I'm going to call this section, this lesson, if you will, composition, structure, and change, because I'm trying to tie it back in with the definition of chemistry. This question here, what are some of the ways that matter can be classified, will directly relate to the unit essential question, which is more or less the same type of question. It's close. So there you have it. Please record this on your student learning map. Pause if necessary with any of these slides. If I go too quickly, stop and rewind, a little bit in order to get the content that you need. This slide is one of two that covers the objectives that are going to cover this particular section of material, both in the reading and in the presentation. These first three objectives do come directly out of your book, while they may be slightly paraphrased or modified, not significantly enough to really cause me to worry. So these are, I will say, in your book. I strongly recommend that you actually record these objectives into your notes as we start each new section, because this is a source of test questions. And all of these make wonderful test questions, and this is where I go in order to start to generate tests and test questions. So I strongly recommend that you actually write them down. You can read them here. I will not read these to you, and certainly if you need more time, pause the slide. I will move on. Now, this is the second page of objectives, and I would draw your attention, and I will slow down, and you may end up having to pause on your own, but I would draw your attention to on this objective here, and I have a pen. I can activate my pen to interact with the slide. I would draw your attention to this objective here, this one here, and the third one down here. Notice all three of these objectives have a star beside them, or an asterisk. And that asterisk tells me that this objective has either been significantly modified from what you'll find in the book, so it may not be the same objective, or it is a brand new objective that is not in your book at all in this chapter, but I find that it is specific and pertinent enough, relevant to this chapter, in order to bring this out. So for me, I would like in this chapter, in this section, to be able for you to explain the two ways that energy is involved in change, because we have stated in the definition of chemistry that energy is involved in change. There are two ways that this happens. I would like you to know what they are and what their differences are. The next thing about energy that I would like you to know is to be able to explain the difference between what is called potential energy and kinetic energy, sometimes symbolized a capital PE or a capital K E, just for short. If you run into them, that's what they look like. But I would like you to understand the difference between those, and then specifically potential energy is very useful when talking about chemicals, and so define potential energy in terms of chemical stability. This last objective is an objective that lines right up with your textbook. Again, I may have shortened it or paraphrased it slightly, but not significantly to where you can't recognize it. Moving on. This slide is the first of the content for section 2, and this slide specifically concerns itself with 4 vocabulary terms that are very important to understand at the beginning of our discussion on matter. And one of those terms is actually what matter is. If we're going to be talking about matter, it's a good idea to know exactly what it is. So matter is simply anything that has mass and volume. Volume is just another way of saying that it takes up some sort of three-dimensional space. Whereas mass is simply how much matter is actually making up an object. So you could consider how many atoms make up that object, or if you want to go deeper, how many protons and neutrons and electrons total make up an object. But whatever level you take it as, it's literally the matter that makes something up. So we call that the mass. An element is simply a pure substance that is made up of only one kind of atom. So no matter what size sample you have of an element, all of the atoms in that element are essentially the same. There are tiny minor differences, but the differences do not make it a different atom. There's just, again, slight variation in like the neutrons, really. But what is an atom? An atom then is simply the smallest piece of an element or smallest part of an element that will exhibit properties of that element. I'm going to move on. If you need more time with these definitions, please pause. One other set of definitions, and that is of when you have 2 or more elements chemically combined, we call that a compound. This vocabulary term should be nothing new to you, especially if you have pre-read, which I always suggest you do, pre-read the material before you actually watch a presentation. The presentations, you'll get a lot more out of it and you'll understand a lot more in the context of the broader picture because you've already read it. So compounds. Compounds are 2 or more elements that are chemically combined, and they chemically combine through a chemical bond, which is how electrons and protons and neutrons from each atom interact with each other to kind of hold each other together in a stable arrangement that we call compounds. Like from hydrogen and oxygen gases, we make water, which is very stable, and it stays together as water. So that kind of thing. Now, compounds have smaller, like a smallest particle, like an atom is the smallest particle of an element. For compounds, we call those molecules or formula units. Now, the term formula unit is actually a term that comes out of your chapter 6. And formula unit, though, however, is a term that I would like you to at least hear of right now. I'm not going to ask that you use it correctly all of the time, but formula unit is a specific term that is for the smallest piece or the smallest unit of a compound where the atoms have actually traded electrons in order to form a bond with each other, as opposed to the term molecule, which is much more well known, I guess. And molecule is where the compound is formed when atoms are sharing their electrons. Now, a difference between a molecule and a formula unit here would be, for instance, just as an example, sugar. So C12H22O11. All of these atoms are sharing electrons, and a symbol for an electron is E- because they're negatively charged. They're all sharing their electrons, and because they're sharing them, we refer to this as a molecule, as opposed to sodium chloride. Sodium chloride, actually, they have traded electrons. That's not a very good symbol for an electron there. But they have traded electrons where sodium loses an electron to chlorine, and then that helps to create a bond between the sodium and the chlorine itself. So this would be a formula unit. This would actually be a molecule. It's not about the size of these substances. It's simply about how they actually are formed in that case. When scientists want to study matter, which can be certainly overwhelming because practically everything is made of matter, what do? Well, the easiest thing would be is to let's look at the properties, see what is similar and what is different, and maybe we can kind of separate matter out and start to kind of clump it together into maybe easier studyable aspects. Well, one way we can do this is to look at how much you have. And anytime a property depends on how much you have, we would call that an extensive property. So extensive properties depend on how much you have. What properties would they be? Well, think about volume. Volume is a property that depends on how much you have. You have more, you have less, the volume changes. Mass. Mass, the more you have, the less you have, mass changes. The shape, more you have, less you have, shape changes. The amount of energy present, as far as in a substance, will change with the amount of a substance. So all of these and more are considered extensive properties. I have always considered the extensive property argument in terms of like an ice cube and an iceberg. And then if you can tell me what the difference is between an iceberg and an ice cube, then you know what an extensive property is. Because the only difference between an ice cube and an iceberg is essentially how much you have, because they're both made of frozen water. And so it's just a difference of how much. Any difference between those two is considered an extensive property. Well, what's the opposite of extensive? Well, the opposite of extensive would then be intensive, and that's the next property. So here we are with intensive, excuse me. So intensive properties, it doesn't matter how much you have, it matters on what you have, the type of matter. So what type of matter, right? I'll say it again, what type of matter? And so the type of matter is, do you have water or do you have hydrogen peroxide? Do you have table salt or do you have something like ice melt, which is like rock salt that you throw down on your sidewalks that is not really food grade? So, which is it? And these properties, depending on what you have, are things like FP, which is freezing point, MP, melting point, the temperature at which something freezes or melts. Boiling point, condensation point, these are all temperatures. And water will melt, freeze, boil, or condense at a particular temperature, and hydrogen peroxide is a different temperature. Sodium chloride is one temperature, calcium chloride is a different temperature, and they're all four different from each other. Why? Because they're all four different types of matter. Density, the density of these substances is different because of the type of substance you have, whether or not they will conduct electricity, whether or not they are flammable. It doesn't matter how much you have, it just matters that you have it. And so I consider, if I want to go back to the ice cube and the iceberg, what is the same? What is the same? And if you can tell me what is the same between the ice cube and the iceberg, kind of have them backwards there, but iceberg and ice cube, then you know what an intensive property is, because those properties will rely on the fact that they're made of water. And any property water has, both of these will have those properties. Those are intensive properties. But what other properties can we look at? Let's move on. Aside from looking at how much you have or what it's made of, we can also look at properties like physical and chemical properties. So physical properties are properties that can be observed without changing the substance's identity. So that's, without changing it. So what does that mean? Well, let's consider water. When you study water, it's water when you start, and it's water when you're done. So start equals water. When you end, you still have water. If you didn't change the identity of it, you have looked at a physical property. What are physical properties? Well, melting point, freezing point, all of these temperatures are physical properties because you can freeze it, you can melt it, you can boil it without changing it. It's still water. It's either just frozen solid, it's liquid, or it's gas, but it's still water. What is the mass? By looking at the mass of water, you haven't changed water. And what is the volume that you have? Do you have an ounce of it? Do you have a milliliter of it? Do you have a full liter of it? The volume, it's still water. Color, area, shape, flexibility, all of these things. These are all physical properties. Now, when we go to physical changes down here, so here's physical changes, realize changes do not involve, again, changing the substance's identity. It's water when you start, it's water when you're done, but there's a change that occurs that tells us more about water than we knew previously. So when we melt water, now melting point up here, if I come back up here, so let's kind of come all the way back up here, right? Melting point is a particular temperature of which something freezes or melts, in this case, melting. Well, melting is an actual change. So notice we went from like a noun, melting point, which describes something, to a verb, melting. So the change is like the verb version of a property. It's the action. It's not a description. It's actually an action. So boiling instead of boiling point, vaporizing instead of like a condensation point, or again a boiling point. Truthfully, all phase changes are actually physical changes. Is it breaking? Is it bending? As opposed to like shattering? And many, many more physical changes. So a physical property is like a noun, and a physical change is like a verb. And all of these describe, remember, a substance without changing it into anything new. Frozen water and gas water, water vapor, same thing. Now, states of matter, this is kind of like the in-class slide that reminds me to go to a website. All right, so a website. And I would search, like just use Google and search for PhET simulations. If you want to see these, PhET simulations. PhET stands for something, and I can't remember exactly, something, educational, whatever. It comes out of the University of Colorado, and when you look under PhET simulations, you would look under phase change. I think there are actually 2 simulations, and you want, I think, the one called basic. I was not able to load it and get it to function within a video like this, so if you want to see it, I would direct you to that, and you would simply toggle. You have a selector switch, you have a can that has particles in the can, and they're moving around slowly, fast, or some kind of intermediate speed, and they have an ability to either add heat or cool it down. And you can watch how the motion changes of these particles, and that's how you can look at a solid or a liquid or a gas and see what the phases look like from a particle point of view. So that's what this particular slide is referencing. It's going to, like, searching or going to a direct website to look up these simulations, and they're interactive. You can change things. You can change what the particles are. You can adjust the phase right off the bat. So a lot of cool things to do there. This is simply a static image of a solid, liquid, or gas of water, just showing you how the particles vary. In a solid, the particles are very, very ordered. Here, if I change the ink color, okay? See, notice how ordered they are. They are very structured as a solid. Notice in a liquid, the particles are almost as close as they are in a solid, but they're not really ordered. They're much more random in here, as opposed to this particular structure. Notice, this structure is repeating. And this is, by the way, why water is a crystal. This is showing you the crystalline structure of water. In a liquid, there is no structure here. There's just, it's just random. And gases, they're all far apart and they don't touch at all, so there's no touching in here at all. And they would actually be moving very fast in all kinds of random directions, wherever they're going, they'd be moving very, very fast. Phases or states of matter. This again is just allowing us to look at some of the phases or states of matter after that simulation to include what a solid is. Well, solids are pretty much defined as anything that contains definite shape and definite volume. If you have a brick and you put it in a bucket, it still retains the shape of the brick and the volume of the brick. It's a solid. Likewise with an ice cube before it melts. Particles in a solid are packed very close together with low energy. They really only vibrate back and forth. They can't change positions with all of the atoms, and you would see this in that simulation. They retained a fixed position. They stay, whatever the particle is right beside them, as long as they're a solid, that same particle will always remain beside them. So, if you have 3 particles in a row and they can vibrate back and forth, however, the particles will always be, if you number them 1, 2, 3, particle 1 and 2 will always be together, and particle 2 and 3 will always be side by side, fixed positions. And this is true in solids only. And they have geometric arrangement. Many solids are very geometrically ordered like water, and many are crystals. Some are kind of a little bit more clumpy to where it doesn't look like a crystal, but it's still arranged fairly commonly. Whereas a liquid does not have any definite shape, but it does have definite volume. So if you have a gallon of water, you have a gallon, that's the volume. But if you pour it on the floor, it tries to take the shape of the floor. If you put it in a bucket, it takes the shape of the bucket because the particles are free to move around. And so that's where the shape can change, but the volume cannot change. Here it says particles are packed loosely together. However, they can slide over each other because they have enough energy to move around and move past each other. They will stay in relative contact with each other, but they do not have to stay in fixed position. So particles 1, 2, and 3 are now able to be intermixed with particles 4, 5, and 22, or whatever, because they can all move around. And they can all slide over each other, and so they do not stay in a fixed position. And they have a relatively random arrangement. And then gases. Gases have no definite shape or no definite volume because gases will expand to fill the container, so the volume changes, and no definite shape, they always take the shape of the container they're in. The particles are spaced very far apart, moving in all directions, and they have high energy. Some of these particles may collide, but they do not stay in contact. So that'd be like pool balls bouncing off of each other on a pool table and sending that one off in that direction. They do not have fixed positions, and these particles move in straight lines. There's no reason for them not to move in straight lines. Now, plasma is actually the fourth state of matter. It's really beyond our discussion. But what is plasma? Solid, liquid, gas, plasma. Well, plasma is simply superheated gas. It's ionized, meaning some of the atoms have lost their electrons, and so that just creates an ion. And there's just tremendous amounts of energy to cause these electrons to actually just shoot away from the atoms that they should have belonged to. Stars are made of plasma, so it's not very common on the Earth, but it is very common in the universe. So really, we will not talk about plasma other than acknowledging it's the fourth state of matter. One thing we do see, I'm sorry, I made the X there, but one thing we do see on the Earth, which is fairly common, is that lightning, I'd forgotten this statement was here, but lightning is actually a form of plasma because of the intense heat around the actual bolt of lightning, which lightning is invisible, but we see the plasma glow of the air around the stream of electricity, and so that is actually plasma. So it's common on the Earth in the form of lightning, but of course it's dangerous. Okay, if it's not a physical property, it's a chemical property. And chemical properties will describe now how the substance changes into a new substance. So it was water before, but somehow we turned it into hydrogen peroxide. It was sodium chloride before, but now we changed it into, say, sodium bromide and HCl, hydrochloric acid, somehow. So we must have combined it with hydrogen bromide to make it all work out. So we kind of rearranged all of this, and we changed sodium chloride into a brand new substance. So that's what chemical properties are. How does it change now into something new? We change its identity. Well, flammability, will it burn? Corrosiveness, will it corrode? Oxidation, will it oxidize? Like shiny aluminum that after a while left outside, it's dull. That would be oxidation. Rusting, anything that has iron in it will actually rust, and that's a form of, again, corrosiveness and oxidation, which is rusting specific to iron, so iron is Fe. Those are all, and just a short list of chemical properties, but all of these describe the ability of substances to change. Chemical changes is simply taking, again, the property as a noun and turning it into a verb, and then that's the chemical change. So instead of saying flammability, will it burn, can it burn, is it burning? There's the chemical change. Will it corrode, can it corrode, it's corroding. There's the change. Oxidizing is a change, and rusting is a change. So again, you turn it into a verb, and now you have the actual change. Comparison of physical and chemical properties. I'll allow you to take a look at this. Please pause and read the slide as you will. I am going to move on. This is simply showing a compound called mercury 2 oxide, which is essentially kind of like a colored powder. And when you put it under intense heat, you can't see it, but the oxygen is actually given off, and you end up with silver mercury formed in the test tube down in here. So you end up with actually a silver liquid, which of course right now would be very hot, but you could cool it down. It'd stay a liquid. It's really cool, but it's dangerous these days because of the mercury fumes. Mercury has the symbol Hg, and the mercury fumes can leave the test tube, and then that causes poisoning. We could also show a chemical change. So this is a chemical change of the electrolysis of water. Oh, I'm sorry. This is the electrolysis of water. Oh yeah. I'm sorry. It is a chemical change. I thought it went back a slide. So here we have this unusual shaped tube right down in here. It's shaped like an H, like a weird looking H. And we have hooked to it down here wires, which are hooked to either a battery or some other power source. And so there's electricity, that just a very mild current that runs through the water here. And what it can do is it can split water from H2O into hydrogen gas and oxygen gas. Now this is not hydrogen peroxide. This is hydrogen gas and oxygen gas. It's different. And this is breaking water down, and so this is a chemical change, and this particular chemical change is simply called electrolysis, using a mild electrical current to break the bond. When we describe chemical changes, we may employ a shorthand method called a chemical equation. Parts of a chemical equation is really what this slide is about, which is simply a shorthand description of a reaction where a chemical change is taking place. For instance, the one below. These two substances here, written on the left-hand side of this arrow, so of the arrow. These are called reactants. It's what you start with. It's the starting material. The arrow simply means to produce, okay? And then what does it make? It makes these things called products. So reactants make your products, and that's what you end with. And the arrow simply means to produce. So reactants on the left, products on the right. Reactants make products. And it's written always this way, where the arrow always points to the right. And that's just a common way these things are done. That's how you read a chemical equation in its basic form. The triangle, by the way, in this case simply means you got to heat it up. That's a shorthand way to say heat it up. Get the Bunsen burner out, get the flame out, put it on a stove, whatever you got to do. Okay, so here's the stuff that's not necessarily in your textbook at the moment, and this is energy. I know this presentation is getting long. We only have just a few more slides to go. Here again, you can pause, stop, come back to it when you need to, or you can power through if you want, like we would do in class in some cases. Okay, here we go with energy. So remember that energy is involved in all change, whether it's a physical change or a chemical change. Energy is involved. Energy can be involved two ways. It can be involved called exothermically or endothermically. Exothermic is a term you should have heard before. Of course, you would not necessarily have read it in your chemistry book, but this is a term that is common to many sciences. Exothermic is simply the release of energy. So energy is released. Think about a campfire, an explosion. These are very common ideas about you're going to get energy out of it. All right, you don't want to be too close to a fire. You get burned. Too close to an explosion and energy, of course, can harm you. So the freezing of water, however, means energy must be released from water so the temperature can go down and water can freeze. Anything that is solidifying has to have energy leaving it so the temperature can go down and the particles can attract each other and solidify into that solid arrangement that we talked about earlier. Well, what if energy is not released? Well, if it's not released, then we call it endothermic. Endo meaning kind of within. And this is when energy is absorbed during the change. This would be like something melting. If you have an ice cube and it wants to melt, you have to put energy into it to raise the temperature. Now, nature can do that by just setting an ice cube on a table, and there's all kinds of energy around the ice cube, and the ice cube can absorb that energy and melt. Most, not all, but most cooking is endothermic, like the frying of an egg, frying of bacon. Great, now I'm hungry. When you boil water or boil anything, you have to put energy in, again, to raise the temperature. When you get a sick stomach and you take an antacid, like a Tums or a Rolaids or a Pepto-Bismol, that when it goes into your system, it actually cools your stomach down. That's not why you get better, but in the action of neutralizing an acid, which is what an antacid does, it actually absorbs energy, and so your stomach actually experiences kind of like a cooling sensation as energy is absorbed away from it. So the reaction of antacids. Whenever we heat a test tube, anything that we have to heat is an endothermic reaction because we're putting energy into it. Moving on. Now there's another way that energy can be involved in all change, and that is the two ways called kinetic and potential. Kinetic energy is often symbolized with a capital K and a capital E, whereas potential energy is symbolized, PE. What is kinetic energy? Well, it's simply anything that possesses energy because of its motion. If anything is in motion, it has energy because of that motion, and that's simply called kinetic. Kinetic comes from a Latin term, kinesis, and kinesis means motion. So think about getting hit by a pitch. If you're on a softball or a baseball team, or if you're playing intramurals, and you get hit by a pitch when you're batting, that hurts. Why? Because that ball, whatever it was, kickball, baseball, softball, that ball had energy. It was moving. If the ball wasn't moving, and you touched it, it wouldn't hurt because, again, no kinetic energy there. Atoms in motion also have kinetic energy because of the motion. And the faster something is moving, the more kinetic energy it is. That's why if you have a kindergartner throwing a pitch at you and it hits you, you should kind of shake it off. But if you have someone on the varsity softball or baseball team and they pitch a ball and it hits you, it's going to hurt. Why? Because it's moving faster. The faster it's moving, the more kinetic energy it has, the more change that can result, and that change, of course, with you and me is a bruise. Otherwise, if it's not moving, we call it potential energy. This is energy resulting from either what it's made of or where it is. So this is the infamous, if you have a cliff, so here's my cliff, and here we are at the bottom of the cliff. And there is a boulder perched precariously at the top of this cliff, we may be worried. This is our worry look with all that worry lines coming off of us, because it has the potential at any moment to fall and maybe cause some change down here, which may result in hurting us. But that is because of position, because this boulder has a particular height difference between us and the boulder that equals a lot of potential energy, a lot of ability to cause change. A gallon of gasoline is highly flammable. Even when it's not burning, it's highly flammable. So that is a lot of potential energy. It could be explosive, right? If a match came near it, because of what it's made of. And so composition or position. Now, the gasoline, holding it, at the top of a cliff, certainly the gallon could fall and it could hit something down here, but really gasoline is more about the composition, not necessarily about a gallon of gas falling down to the bottom of a cliff. Although that's potential, but it's not like really the potential of gasoline because of its composition. Now, and I just wrote over a bunch of this, so let me just erase all of this for the moment. The lower the potential energy, the more stable a chemical. So water has very low potential energy and it's very stable, doesn't really do anything. Whereas gasoline has a high level of potential energy and it's very unstable, so it's flammable, it can be explosive and all of that stuff. There's a compound called nitroglycerin. Nitroglycerin is very unstable and it has a high level of potential energy. Nitroglycerin is something that's so unstable that if you had a test tube of it and you shook it up, put your thumb over the top and you shook it up, it could literally explode right in your hands. Water, however, is very stable. You can do a lot of things with water, and it's safe. It doesn't really do anything. Okay, now there is also a conservation law, very much like the law of conservation of matter. There is the law of conservation of energy. Now, a lot of students get these two terms confused, and I get a lot of the conservation of energy stuff on the test for the matter law. So be careful on that there's a problem there. This simply states that the total energy in a closed system, closed means energy can't get in and energy can't get out. It's sealed up, it's closed up. When you have energy in a closed system, the amount of energy does not change. You can only transform that energy into different types of forms. So what are forms of energy? Well, think about the gasoline. The gasoline is a chemical energy. If you burn that gasoline in your engine of your car, you can turn that into mechanical energy, moving parts. Those moving parts generate friction, which is heat. Gasoline burning in an engine to move the car, hot engine, hot exhaust, etc. And so the gas results in wheel motion, but it also results in a lot of heat, which really doesn't help your car out too much. So that's the idea behind the law of conservation of energy. All conservation laws, okay, so all conservation laws are about the amount of whatever it is the same at the beginning, at the end. And that's really all conservation laws. And then you modify the conservation law to whatever specifically you're talking about. Nature has a lot of evidence of conservation in many, many aspects of it. And so we have lots of conservation laws that describe that in science. Okay, classifying matter. We can classify matter a few different ways. One way is, of course, extensive and intensive properties. Another way would be to look at physical properties and chemical properties, which is different. Also, we can look at simply just what it's made of. And, what is matter made of? If matter is made of a physical mixture, which is simply the physical combination, so I'm down here, physical combination of two or more types of matter, then it's a physical mixture. This would be like a bowl of cereal. So you have Cheerios, and you have the milk, and you have the sugar. That's a physical combination of matter. You just put those three things together in the same bowl, if you will. Every sample will have a different composition. This is why when you're eating cereal, sometimes you get a bite of Lucky Charms with lots of marshmallows. And then sometimes you get a bite with mostly cereal bits. If you're eating Cheerios, you get a bite of Cheerios with a lot of sugar and a bite with very little sugar, because the composition can change from one part to another of the sample that you have. And that's just the property of physical mixtures. A bucket of sand is the same way. It's not a chemical because the composition changes from one spoonful of sand to the next. It's made of different bits of rock and seaweed and glass and everything else that you could find in a bucket of sand. Each part of the mixture on this third part down here, each part of the mixture will retain its own properties. So the sugar still tastes sweet, the marshmallows still taste like marshmallows, the milk still tastes like milk, and the cereal bits in Lucky Charms still taste like cereal bits. They all keep their own properties. They don't mix their properties. You just get them all at once, and so you can kind of taste many of the flavors combining together. But they're still all there, and they're still their own flavors. Any part of a mixture can be separated by physical means, i.e., for example, getting the salt out of salt water is actually not all that hard. Basically, just take some salt water, okay, so there's your salt water, and simply evaporate the water. If you evaporate the water, the salt will stay behind, and you'll have an empty container with only salt. The water's lost. Now, if you want to capture the water, you have to have a way to capture the evaporating water as it comes out. But if you don't need the water, just simply evaporate it. Or if you don't have a lot of time, you could boil it with a candle, like with a flame or something like that. And boiling it would make this happen just that much faster. But the salt will stay behind and the water will go away. And then you've effectively just physically separated salt and water. So not really difficult. There are two ways that we can classify matter. They are heterogeneous and homogeneous. Heterogeneous is where the parts look different. That's not a good D. So how about here? Different. And homogeneous is where the parts look the same. So Lucky Charms, so cereal is over here, and this would be like a glass of salt water. Even though it's salt water, you can't see the salt in the water, and a glass of salt water would look identical to a glass of fresh water, and you would only know upon tasting that one has salt and one doesn't. So that's homogeneous. You can't tell from just looking at it that there is more than one thing there until you do some further testing. Physical mixtures, so this is a continuation there. Physical mixtures can be separated by physical means. Physical separation is possible because each part of the mixture retains its original properties. You can do mechanical separation like in Lucky Charms. You can actually physically pick out the cereal bits or the marshmallow bits. Children do that all the time. I remember when my son was very young in a high chair, he understood the marshmallows were sugary, they were sweet, and so he would just hand pick out the marshmallows and eat them, and then you would just have a bowl of cereal bits, which are really honestly not all that tasty. You could filter something like using a coffee filter. So you could strain a dirty water through a coffee filter and it would clean up the water quite a bit. You could use distillation, which takes advantage of different boiling points. Water boils at 100 degrees Celsius, alcohol boils at 70 degrees Celsius. So you get the temperature up to 70, only the alcohol boils and it'll boil away, leaving the water. As long as you don't get the temperature up to 100, water will stay behind. Chromatography, you can separate the colors of ink out of a black pen by using chromatography. Simply a kind of a sheet of coffee paper. You just flatten out a piece of coffee filter paper and then put a dot of ink on it and then allow the coffee filter to actually touch some alcohol or some other, even water sometimes works. And as the alcohol or the water soaks up through the paper, it dissolves the ink and starts to separate the ink out into the various colors that make up whatever color you have. Most inks are a mixture of pigments. They're not just one true pigment. You can use density. Things are just heavier and more dense than others, and you can use that to separate things out. If something is magnetic and something isn't, you can actually use a magnet. Or will something dissolve and not dissolve? Think about having sand and salt all mixed together in the same cup. How can you separate the sand and the salt? Well, add water. If you add water, it'll dissolve the salt, but it will not dissolve the sand. So now you have salt water and sand. Then put it through a coffee filter. So you pour it through a coffee filter. The sand stays behind and the salt water goes through. So that's H2O plus NaCl. I know this is bad, but my pen's kind of malfunctioning. And the salt stays behind, and then the salt water comes out. And if you catch it in a glass down below, then you now have salt water and you have sand. It's now separated. What can you do with the salt water? We're back up to taking the salt water and you heat it up with a candle of some sort. That's a candle. And the water will evaporate away and you leave the salt. So again, physically, you've just separated it using a water, a coffee filter, and a way to heat it up. So there you go. Everything is just physical separation because nothing really mixes together. They're just in the same spot. Now, the other side of this classifying matter is pure substances. Pure substances have only one kind of matter present. It is not a mixture. It is one true pure type of matter. An example would be sugar or salt or just the element sodium. All of these would be considered pure substances. Now the difference, every sample of the substance has exactly the same composition. So it's not like a bucket of sand where each teaspoon is slightly different. In this case, in a sugar bowl with the sugar, every teaspoon is exactly the same as far as what it's made of. Now, if you have a half a teaspoon and a full teaspoon, that's not what we're talking about. We're talking about what it is. Everything would be just sugar in that sugar bowl. Now, you can only separate pure substances by chemical means because you're going to have to break bonds, and bonds take energy to break. So you can only separate them by physical means. You cannot separate them through physical properties. Now, pure substances come in two forms. They can either be elements or they can be compounds. Elements are the most basic of all substances, and compounds, remember, are two or more elements combined together chemically. Here is a very simple chart of how matter can be classified. And up here, starting at the very top, matter could either be a pure substance or it can be a physical mixture. If it is a pure substance, it can either be an element, the simplest, or a compound, two or more elements bonded together. Over on the mixture side, it can either be homogeneous or it can be heterogeneous. Now, there is actually a subclassification of homogeneous, and that would be a solution. A solution would be like a salt-water combination where it actually appears as one form of liquid, and that is a solution. Heterogeneous mixtures actually come into subclassifications. One is called a colloid, and one is called a suspension. Colloids and suspensions differ in the particle size. Suspensions have very large particles, colloids have much smaller particles, and solutions have tiny particles. Colloids do not settle upon standing, suspensions do. Colloids would be like toothpaste and fog, for instance. And let's see, another colloid would be mayonnaise. A suspension would be like a mud puddle or Italian salad dressing. So Italian salad dressing, you got to shake it up to get everything to mix so you can pour it on your salad. Otherwise, you just pour out oil. So that's a suspension. You can temporarily mix them up, but they'll settle out if you leave them alone. Colloids, you don't have to mix up. You don't have to shake up your toothpaste to use it. And solutions always stay mixed all the time. Here's just a yes or no if you had to use kind of like a key in order to figure things out. You can look at this if you want. I'm going to move on. This slide is simply reserved for me to actually interact quickly and make a chart for you. So if I wanted to make a matter classification chart for my own, I would start up here and I would say, well, matter is right there. And it can be classified two ways. It can be classified as a physical mixture, or it can be classified as a pure substance. Physical mixtures over here can be classified two ways: heterogeneous or homogeneous. Heterogeneous can be subclassified into suspensions. Remember, you can temporarily mix them, but they'll settle out on standing, or colloids. Homogeneous can be subcategorized into solutions. Over on the pure substance side, and by the way, this is all physical combinations, and they will all be physically separated. So all physical, so separated. Over here on pure substances side, pure substances come in the form of either elements, of which there are 118 of them, by the way, or compounds. So with elements, while this is not necessarily a subclassification, remember that atoms are the smallest parts of an element, and with compounds, typically we call them molecules or formula units. So, that's just the smallest part. It's not really a subcategorization, it's just a small part. So this would be a way to show graphically how matter is classified. And it's a great way. If you can explain this diagram here with all the details, then you can handle the unit essential question for the chapter very easily. You can read over this. It just gives you a few examples of heterogeneous and homogeneous mixtures with a couple of pictures. And then this ends the entire chapter. I know this has gone on quite long, but there's a lot to do, and normally this would be 2 or 3 days in the classroom, interacting with the board and doing homework and all of that. So there you have it. This slide here just tells me that I am at the end of section 2 and section 3 will follow, which is the last section, and it would be the last video, by the way. So thank you for your attention. If you have any questions about anything that was presented, please get in touch with me, Mr. Spencer, when it's convenient to you through any of the methods of communication through school. Thank you very much, and we'll see you in the third video if you need it.